Thank you for joining us for our second talk in the 14-15 SIG webinar series. Today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphones enabled to use the chat window to type in your questions or to communicate with others. Presentations in this series will be approximately 50 minutes in length, with questions and answers following during the remaining time. Today we have Professor Jed Brown. Jed was raised by wolves in a remote part of interior Alaska. He traded homeschooling to become part of the wolf pack in high school. Later on, he defected to become a Nanook at the University of Alaska Fairbanks, earning All-American honors in cross-country skiing. His fondness of skiing and climbing in icy remote places led to his academic interest, in which he wrote the parallel ice sheet model while at UAF, and then later earned a doctorate in science at ETH Zurich, investigating computational methods for ice sheet and glacier dynamics. Gradually warming up to temperate climates, he won the 2009 PLA d'Or Climbing Award for the first ascent of Zhulian West in China's Tianshan, and has subsequently solved high-temperature problems while at Argonne National Lab. He has been a Pet-C developer since 2008 and is part of the team that recently won the 2015 SciAm ACM Prize in Computational Science and Engineering for Pet-C, the portable extensible toolkit for scientific computing. Jed is currently an assistant computational mathematician at Argonne and holds a joint appointment at the University of Colorado Boulder. Today, Jed will share his thoughts and practices on software design and packaging for extensibility, provenance, and sharing. Thank you, Jed.
I'd like to share some ideas about software design and kind of where I see applications going, where I see curating our knowledge about methods and collecting the principles about the physics that we're simulating. And so to kick this off, I have a sales pitch. There we go. All right, so introducing the browser Firetran. So Firetran is a web browser, and it renders HTML 10% faster than Firefox or Chromium. Sounds pretty good, eh? Well, what if I told you that it's only faster if there's no JavaScript? If you want to use JavaScript, you have to recompile. If you recompile, it's not really faster anymore. The character encoding is compiled in. There's mutually incompatible forks, and those forks have different bugs. It's not clear where to report them. There's no confusion on proxy dialogues. All you have to do is edit a file and recompile, and you get a different proxy. For security, the HTTP and HTTPS are mutually incompatible, so you can compile one version of the browser to view your insecure page and a different version of the browser to view your page. The address goes in a configuration file. There's no GUI, so you run the executable again if you want to render a different page. Now there's a tickle script that manages a configuration file, because that was kind of a hassle. And you know, the way we're going to make this all better now is we're going to extend the script so that you can recompile Firetran with the optimal features for each page. Well, needless to say, Firetran struggles gaining market share. And yet, a lot of these practices are basically the status quo for a lot of our scientific software. Now, why do we tolerate that? Is scientific software really different? Is this just Stockholm syndrome, and you know, we're accustomed to doing it in this bad way, and you know, we can't see that all the other software that we use doesn't have this insane workflow? Well, that's sort of the motivation of what not to do. So I'd like to kind of start at a high level here. What are some directions that we're going in computational science? So definitely our models are going towards more multi-physics, multi-scale phenomena. We wrap new levels of analysis around it. So data assimilation, inversion, uncertainty quantification, these things become more important. Often we're targeting questions like risk-aware design, decisions, how to build a field study, things like that are target problems of our computation these days. So with these more complicated problems and trying to do more sophisticated analysis, we also have deeper software stacks. So there's more levels of library. We're pulling in different models, often written by different people. There's a lot of forms of extensibility. And we can end up creating artificial bottlenecks by various choices we make in our organization software. So a very recurring theme, one that troubles me quite a lot, is the compile time configuration. And sometimes I call this Fortran disease, because in especially old versions of Fortran, you had very limited ability to create runtime configurable systems. So the status quo was very much to have certain special names. The build system would decide which implementation to begin. Now, some people would justify that in the name of efficiency. So they would say, I want these static function calls, or I want a certain kind of inlining. Often that's done without a very objective evaluation. So very frequently, you can choose a granularity of inner. Often there's an overemphasis on efficiency. If we were to design our interfaces with an appropriate granularity, then we may not need the level of inlining or static calls that people are using to justify. I also think that sometimes it's okay to give up a little bit of efficiency, say a few percent. And in many cases, that's what we're talking about for those inlining techniques. Templates are often put forth as a way to get the high performance, to cause the compiler to do this sort of inlining. But templates, and I'm thinking C++ templates here, you end up compiling a combinatorial number of variants, and that takes a long time. The time for the compilation is something in the critical path of your workflow. Also, the size of binaries grows a lot, and it's still not runtime extensible. So I'll talk a bit about plugins, why I think plugins are a really powerful design principle. Templates don't play real well with that. So I won't argue that they don't have their place. They do have their place, but templates in public interfaces, I think, are usually undesirable. So compile time configuration, it also compromises the ability to do online analysis. So I'll talk about this a little bit more, but you're basically creating artificial bottlenecks, like writing things out to files just so that you can read them in from a different program or in a different configuration. And there's no fundamental reason for that. If you get rid of the compile time configuration, you could have all of the phases of your analysis in one executable, for example, and then you could exchange that information in memory in a reliable way. The compile time configuration also ends up offloading a lot of complexity to scripts and workflow tools. And doing that tends to be more difficult to debug. You now have to maintain scripts in multiple languages. You have your compiled code and the scripts that work with it. There's no type checking between those, but they have to maintain consistency. Often those tools end up being architecture specific. So you have to, say, maintain one for a different batch queuing system than another. You may interact with the system in a different way on a laptop than on a supercomputer. And I think that's also very undesirable. It adds complexity. our overall goal is to control complexity. So any complexity we add is a bad thing. Compile time configuration also limits the ability to automate and test the quality of calibration. And so in a lot of geoscience models, calibration is a somewhat ad hoc process. It involves expert opinion in places. It's not as simple as solving a particular formally specified inverse problem, for example. Also, just maintaining consistency between all of the artifacts, all the steps of your analysis pipeline, that complicates the provenance, and it makes it difficult to reproduce results. So I think compile time configuration is really a bad thing, and we should try to avoid it. I would also look at the state of model coupling. So the current status quo in many ways is that we have these hero codes. There's a visionary scientist in the domain that started some project. Perhaps they've gotten a lot of help over the years, but they envisioned a lot of the issues that would show up within that domain. The package also had the freedom to make a lot of assumptions about its environment. And the thing is, often within those single domain areas, a lot of the research tends to be pretty mature there. And so a lot of what ought to be low-hanging fruit, a lot of the gaps in our knowledge are in between the existing models. And so to investigate those kind of questions, we want to be able to put models together. So models typically operate at different scales. It's very rare to have very different physical processes that happen to be at the same scales. And often those different processes have different uncertainties. And so if we want to be somewhat rigorous about what we're solving, we want to be able to control the splitting error, have some reliable method where we can, say, estimate the errors in what we're predicting. Then we have to deal with these disparate scales and perhaps different statistical models. So even with the best behaved components, that coupling problem is hard. If we have poorly behaved components, then it tends to be so rickety that very few people can do it, and it's very hard to reproduce. Then our inferences are not very objective. So in order to deal with this, I think it's very valuable to think like a library developer. So minimize any assumptions that are made about the environment. Get rid of globals, make limit the side effects of anything that you could do. Make them as local as possible, as explicit as possible. So if we look in other areas outside of science, there's a huge number of success stories for packaging something that was normally thought of as an end user product into a library. So compilers, there's the LLVM project, for example, that's been very successful by packaging this thing that normally is an end user, it's an application, and by making it a library, it stimulated a lot of innovation. There's a lot of new programming languages and new software tools that build on it as a library. Web browsers, similarly. If we look back in the 90s, all the web browsers were just applications. Now the rendering engines are available in libraries, and they get embedded in other products. That's useful. Similarly with databases. SQLite, for example, is extremely popular. It's a lightweight library that has this full functionality of a database. So there are cases in scientific computing as well, but perhaps these in other areas will help make the case. When we do a simulation, we say publish on some results. How do we capture all the configuration knobs so that that experiment can be reproduced, hopefully by a different person even? So compare the complexity of having a single runtime configuration file for, say, a multiphysics simulation. Comes from multiple packages, but if those packages were exposed as libraries, had a good runtime configuration interface, then it's entirely feasible, and there's a number of examples within scientific computing of this, where you can have a single configuration file that passes the information into the various libraries. On the other hand, you can have a compile time configuration, multiple build systems. You perhaps have scripts that write into various places in those build systems to get everything configured. Various files are passed between stages, sometimes rebuilding between stages. So clearly the reliability of the second approach is worse. Now, an issue with libraries, all of the transient dependencies also need to be good libraries. So it doesn't do me any good if I'm exposing a good library-like interface, and yet part of doing what I'm supposed to do is to call some lower level library that has to be recompiled for every configuration. So really, every step along the chain, all of the dependencies should be exposed as good libraries. If you do that, everything sort of falls in place, and lots of problems go away. Another issue is how to deal with custom modifications. So often we'll have a simulation package, and some researcher picks it up, and they want to do various simulations or analysis with it, and something that's not exactly what was already provided within that package. So one kind of common approach is they just clone the source and they start modifying the source. So the trouble there is, how do we keep track of those changes? How do we allow other people to use those changes? And can we send those changes back upstream? So plugins are a way of isolating that change, and in fact, you can retain a lot more ownership over that, say, added functionality. So with source modification, usually it just dies. Probably 90% of cases, it just ends up dying. That is, the changes that were used for a particular publication never make it back into an upstream product, never really available for other people, and probably the results in the paper are difficult to reproduce. And it really takes dedicated effort in order to get those changes back upstream. Now, if the upstream package was written as a with support for plugins, then it's perfectly reasonable to have this added functionality, the true contribution towards the paper. You can put that into a plugin, and you can take ownership of that project, or you can contribute it upstream. Either way, it's easier for upstream to accept, because usually something implemented in a new plugin doesn't disrupt the existing functionality. And if you retain ownership of that part, you can collaborate with other people on it. It's easy to distribute. It can be maintained for new versions coming from upstream. So all of these aspects end up working better. I made a comment earlier about artificial I/O bottlenecks. So quite a number of places where I see people talk about big data, talk about I/O bottlenecks. It's actually an artifact of the workflow. So people may have a workflow that has multiple stages, and the way to get data between those stages is to write it out to the file system. So in some cases, this seems kind of unavoidable. If, say, a human has to make specific decisions between those stages, but in a lot of cases, you know what you're going to do next with the data. And so writing it out to disk just to read it back in and convert to a different format and write out again um, is it's really a waste of I/O bandwidth. So on current machines, and this is a actually relatively good estimate across most of the top machines these days. It takes about an hour to read or write the contents of volatile memory. So if your simulation uses most of the available memory and you want to checkpoint the complete contents of what's in your application, it takes about an hour. Now, we can conclude there that global storage as an algorithmic mechanism is basically dead. So if we have a scalable code, something that scales algorithmically, we can just run on more cores and it'll still run efficiently, then it's much more efficient to run in core on a larger machine. Now there's no I/O bandwidth. We can stack up all the levels of the analysis pipeline, and we never have to deal with disk, not until the final stage, whatever the human ends up interacting with later. So if you were to run out of core on the full machine, that is, you don't have any more cores available, then you would end up blowing the annual compute budget in basically one shot or a very small number of shots. So suppose you have an Insight award, maybe it's a few tens of millions of core hours, but if you run on 1,000,000 cores and it takes an hour each time you write or read the contents of memory, you're going to burn through that allocation really fast. So we're just not at the point where, outside of a couple rare cases, where science applications have the compute budget to be able to run on the whole machine, run a problem that can't fit in core. So by passing data in memory, we can circumvent the I/O bottleneck. We get rid of a certain number of the big data problems, and what we're left with is dealing with, say, irregularity of the data, dealing with interesting characteristics of the data, but not just the size, and mostly not limited by I/O bandwidth. So they're interesting problems. I commented earlier on transitive dependencies, this concept of nesting. So I have some I have some library. My library depends on another level. Perhaps components get used from multiple places. So perhaps the highest objective of software is to control complexity, and encapsulation is a really important part of that. So if your application calls my library, you shouldn't have to deal with whatever libraries I call. So the complexity from those pieces, anything further down the line, really shouldn't bubble up to that top level. It shouldn't disrupt the way that you talk to my library. I'm serving a certain purpose for you. So if you have to reconfigure those transitive dependencies, it breaks the encapsulation, because now up at the top level, just depending on what you need to do, the library that I use indirectly would need to be reconfigured, and that's just a terrible workflow, and it's not controlling complexity. So it's also worth noting that a single library can be used by multiple components in an executable. So, for example, you can have a diamond dependency graph where a certain component, be it, say, a graph partitioner or a solver, gets called from, say, from multiple physics models. So you might have surface processes, lithosphere dynamics, possibly mantle. Each of those components may end up calling into, say, the same solver's library, or graph partitioning, these kind of things. So we need that the version and configuration of any of those dependencies be able to be used from each of the components. So, for example, if we do, say, surface processes and lithosphere, and those both call into PETSI we have to be able to use the same version of PETSI in both places. And so we, well, we do everything we can to make that possible, and in general, that works just fine. But it's something that needs thinking about. Onto packaging and distribution. So developers very frequently underestimate the challenge of installing software. Basically, anyone who only builds their own software, who doesn't have a lot of external users, will be surprised and possibly overwhelmed when they get external users. So the trouble is the user experience is really impacted even when it's the user's fault. So the user has a broken environment, they have broken compilers, their MPI doesn't work, they're mixing together, say, different versions of MPI, issues like that. It manifests itself as a failure to install your package. And you might end up working things out and they figure out what the problem is, but it still disrupts things. And a lot of people won't write in. They won't ask the questions. They'll write it off, and blame something else. So distributing software that is easy for package managers to distribute is very valuable, because the easiest way to get something installed on someone's machine, particularly on the sort of machines we tend to use in scientific computing, is to get it into the package manager, to make it easy for those people to build and distribute it. If you put it there, they have a binary install. The user that comes along and wants to use your package, they don't have to deal with the source. They don't have to deal with building it. It'll be there quickly. So the binary interface turns out to be really essential for that. So if you have a library that gets used by a bunch of, say, other libraries, applications, when that binary interface changes, it requires recompiling all of those applications that use it. So it's acceptable to do that occasionally. And the way you define occasionally depends on how mature the software is and what all of the state of the users. But the package managers should be able to trust when a binary interface will continue to be stable or when it's going to change. I mentioned earlier about user modification. So modifying in the source is bad, causes some fragmentation. Maintaining the local modifications is expensive. It tends to cause some design divergence, and then it's hard to bring things back together. So it's better to contain changes in a plugin. What does a plugin look like?
You have a question, Jed.
Yeah.
So there's a question here that says, by occasionally, do you mean a major release?
Yeah. So there's a concept called semantic versioning, and the basic principle there is you pick some level of your numbering system, and API changes, say backward compatible API changes or binary interface changes, can happen only when that number is incremented. And so some people use this as the first number, normally the major release. Some have it as the second number. So in PETSI, for example, we have a release about once a year that historically we've been doing it once a year. So like 3.4 or 3.5, that allows an interface change. But then we have maintenance releases like 3.4.1, 3.4.2, and so on. And those releases promise to maintain both binary and source compatibility. So people can freely upgrade them as shared libraries. They don't have to worry about build problems, and they don't have to recompile the dependencies. I think hopefully that answers Patrick's question. So it's good to contain changes in a plugin. What do plugins look like? So I would say a key component of a plugin is you create a shared library. Um, with shared libraries, you can register an init function. So you can either have a special name that um, that'll end up getting called specifically, or you can use the built-in functionality with attribute constructor. There's a couple ways of doing this so that it gets called automatically on DLOpen. So typically you'll put those shared libraries in some plugins directory, and your application or higher level library that's providing the plugins will go look and load all of the shared libraries that are sitting in that directory. So something along those lines is the most common way to do it. So that initialization function will register any of the implementations that are available in the library. So for example, in PETSI, we have these functions like PC register, which registers a preconditioner implementation, and for all of the other major objects. So we can distribute shared libraries that way. You don't have to recompile the user code. You can just load these, and they look native. They get controlled through runtime options, which I'll discuss slightly. I'll discuss a little bit later. So using plugins allows you to invert dependencies and avoid loops. So suppose I have a situation where lib_b depends on lib_a. Now I want to add an optional implementation of lib_a that uses lib_b. So I can't put it in lib_a because that makes a circular dependency. I could put it in lib_b, but it might not make any sense in lib_b. It may not make logical sense to distribute in that way. I can make a thing like lib_a plugin that depends on both lib_a and lib_b, and that actually works. It's logically consistent. So an example of this is SLEPC depends on PETSI, and there are certain preconditioners that solve generalized eigenvalue problems. So SLEPC being the eigensolver, we'd like to use those. We can't put everything over in core PETSI because PETSI can't depend on SLEPC. That would be a circular dependency. But it seems a little bit funny to package a preconditioner over in SLEPC, which is really just an eigensolver package. So the way we're working on that particular class of preconditioners, we put it in a plugin.
So Matt has a for you, Jed. I don't know if you can hear that.
Yeah, so the closed world assumption for all lib_b's. I guess I'm not sure exactly what he means here. We certainly could bundle things into lib_b, but SLEPC isn't a preconditioning package, so it would be sort of stepping on their toes or a little bit bastardized to put it in there. Right. Okay. It is possible to do something like this with static libraries, but you have to change the link line. So personally, I think static libraries are anti-productive, and you should tell your computing center, because when they make dynamic libraries not work, it really causes some bad design decisions. But what you can do, you can compile static libraries and put them with a little bit of metadata into some directory, and the tool that figures out how to link, that gives all of the link flags that are needed, can find those plugin static libraries and construct a link line that includes them. Then everything works down the line. But it means you have to recompile or relink anyway to pick up a plugin. So not ideal, but it works. So the highest objective of software is to control complexity. This theme of nested dependencies it's a recurring issue. It's very important that the implementation complexity not leak up into the public interface. So we can do this when we design libraries. We choose good defaults, but we also have to provide a way to configure the inner parts in a way that doesn't pollute the public interface. So the techniques for doing this fall under the moniker of inversion of control. So some specific techniques for that are dependency injection, service locator. PETSI uses a pattern that is often in the literature referred to as service locator. So the idea there is you have some way of saying, I'm going to configure this type using information from, well, in our case, from the options database, but using some runtime configuration information. So in PETSI, all of the objects have a set from options function. And that set from options function consults what we call the options database, which is basically a bunch of strings, but it comes from configuration files, command line, environment variables. There's a bunch of ways to get things into the options database. So there can be multiple instances of certain components. For example, we may have several linear solvers in a given application, some of which are done by, say, a surface process model, some done by lithospheric dynamics model, maybe even subcomponents of the lithospheric dynamics model. And so in PETSI, we distinguish those using a prefix. So we have a special label that we assign to each of those solvers, and then we can control them independently through the runtime options. There are some projects, it's particularly popular in the game space or in like image processing tools, where there's actually a Turing complete configuration language. So PETSI's configuration language is not Turing complete, but it is extensible. And it allows these levels of composition. Having a more sophisticated scripting is certainly valuable in some cases. Yeah, a couple comments on object-oriented design. So I'm an advocate of something called partial implementation. But the idea is, should all errors be compile time errors? So if you pursue that ideal, and say within the functional programming community that is a very front and center ideal, then you tend to end up with class hierarchies that can be fairly brittle. So for example, designing a good general matrix class is actually remarkably challenging. So should matrices have computable entries? Should you be able to get access to the diagonal? Can you apply the transpose? Is there such a concept as a Neumann subproblem? So those show up in certain domain decomposition methods. It turns out there are lots of linear operators that can be applied efficiently that maybe don't have computable entries. It would be very expensive to compute individual entries. Like the cost is basically that of applying it to the operator to each column of the identity. So it's a very expensive operation. Whereas applying the operator to an individual column is quite cheap. Some matrices are dense. If it's large and dense, then you can't reasonably produce the individual entries. You could produce specific ones, but in general, representing the matrix as entries would be very expensive. So different preconditioners, though, require different properties from the matrix. So what should the top-level interface be where you talk to the solver? The solver, if it's going to be dynamically configured, has the ability to choose different preconditioners. And so you end up with this situation where either there's a dynamic cast or some equivalent functionality where you can get a runtime error, or you require that the very rich interface be satisfied in order to go do something that might in fact not rely on that rich interface. So I like partial implementation because it lets you do what's needed. It does defer some things to runtime, but actually the error messages you get at runtime are often much more helpful than what you would have gotten at compile time. Controlling the binary interface. So to start off with, just recompiling code is wasted productivity. So it sucks to have to recompile code all the time, to recompile all the client when you're working on a library. So if you can contain the binary interface, then you can work, say, in implementations for the library, and you don't have to recompile the client code. So discretization libraries, the specific application. And so you can very quickly go from a edit, compile, run cycle of 5 minutes to 5 seconds just by controlling the interface appropriately. So implementation concerns like private variables, virtual methods, they shouldn't force you to recompile user code. And so to achieve this, PETSA uses a technique called a delegator or pointer to implementation pattern. So all that's exposed publicly is this opaque pointer and a set of methods. So if we're not modifying the interfaces to those methods, that is, if we're not breaking the interface, then we don't have to recompile, because all the private information is actually private. It's not visible at all to the user. So in order to achieve that, you get this static function call. So the static function call will often then do a dynamic or indirect function call into the specific implementation. But the incremental cost of that static indirection is generally less than 2 cycles. Often it's 1 or even 0. And it's actually really useful to have a common entry point to put a breakpoint. So that having that delegator pattern is, I think, much better for debugging. And it gives you that nice control over the binary interface. Also, by having a relatively simple type system and something where you don't expose a lot of internal details is really good for exposing interfaces for dynamic programming languages. So this can be exposing something to Python or to Julia, for example. It's much easier. Now, there are cases where the fine-grained composition benefits a lot from inlining. So an example would be if you have a Riemann solver and an equation of state. Those may be fine enough granularity that if you're going to call that in a pointwise manner, it becomes expensive. Similarly, if you have a material model, you call it independently at every quadrature point in a finite element code, that may be too small of granularity, and then you see the performance impact. And so I think that the right technology to address this is just-in-time compilation. And so the tools there are not super mature right now, but the LLVM environment is really provides a lot of promise there, and I think it's a much better alternative to templating, for example, or other methods of inlining. So if we get that up and running, it'd be very good because it would allow dynamic kernel fusion, plugin style packaging, and debugging where it looks like totally dynamic code, which is the easiest, but then the performance of the static, fully inlined code. Finally, it's important for maintainers to provide a good community environment. So I think maintainers should they should encourage the users and the people that might be trying to modify or extend their package a good mechanism for contributing upstream. So one of the most important aspects there is having a welcoming environment for contributions. So the time between someone, say, submitting a pull request, sending a patch to a mailing list, and getting a response is a really strong indicator of how likely people are to stick with that project, to continue to interact with that community. So having a prompt and welcoming response is really important. Some people have a lot of concerns about privacy, or they're worried about someone scooping their work, and so they'll end up not sharing code. And my opinion in this matter is that's really a social problem and best dealt with using social means. So there's very interesting literature on both sides of this, but personally, I think we really advance the state of the practice much better by being open. And in my experience, people tend to recognize contributions and give credit where credit's due. And the rare cases where that doesn't happen, address it as a social problem. It's much more expensive to maintain that privacy. In a number of cases, major tech companies have underestimated the cost of forking. And so if you fork a project, keep it separate for a while, and then you want to integrate later. You want new, or even if you don't want to send anything upstream, you just want the benefit of new things that upstream developed. So the one-way case, that can be very expensive. And in science, we usually don't have the ability to get a large budget to spend a lot of time paying off the technical debt by integrating these changes. So I think it's important for us especially to operate in a way that keeps the incremental cost low at all times. So sometimes a startup can go the other way because either they go out of business next year and it doesn't matter, or they've grown so much that they can spend more to pay off the technical debt. I think providing extension points to reduce the barrier for new development, to have kind of low-hanging fruit that new people can get involved with, and to stimulate some creativity, that's valuable. I'm going to skip a couple slides here about specifically about Git workflows. I'd be happy to discuss that further. So to wrap things up, think like a library developer. Even if you're writing an application, it may in fact be just one part of a given analysis or simulation pipeline later. So avoid all the assumptions you can about the environment. Work with what's given to you. If you can, make everything a runtime decision. Above all, control complexity. encourage contributions. Try to have a plan for creative new directions you didn't think of yet. So plan for the unknown unknowns. And that looks like it's, well, 1:55 or 2:55 your time. Anyway, are there any questions? Things people would like to discuss?
Yes, please go ahead and type your questions in the chat box. I like to let you know, Jed, while you were talking, I did Google Firetran, and he only has 6 friends. Not a popular character.
So there's a paper that I wrote for SICE that it actually covers a lot of these issues, and I should have put it. I should have put a link on here.
You have multiple people typing while they haven't hit return. I want to remind people we will not have a webinar next week. Next month due to AGU. We'll be taking a break, and we'll be returning in January. Matt has a question. Isn't it a big drawback of package managers that they do not test the things that are configured?
I'm not sure what that means. Is that like packaging something that's not a good library? So it's configured in only one way?
Matt, your microphone's enabled if you want to speak. I can open the microphones if you guys want to have a larger discussion on this.
So I just put a link in there to a preprint of this paper, in case people are interested in that. So package management so Matt's question is about variation in HPC environments, and absolutely, package management in HPC environments is totally hokey, and that's like largely the choice of the centers and the stack that they end up building on to have something that's that hokey. So yeah, packaging in those places is challenging, and you tend not to use the package like directly from Debian. They could if they made the environment more sane.
Okay, do we have any more questions? I'm not quite sure whether or not, let us know if you need Jed to clarify anything or you don't feel like your question has gotten answered. Oh, here's one from Eric. So for older, well-established software, time parameters, with complex workflows and compile time parameterization, do you think it's better to try and fix the software or mostly rewrite from scratch?
I think it depends a lot on the package. So the yes, Matt says always rewrite. Um, so often you can take the like core, say, numerical routines. You can take the like the part that was a publishable contribution towards methods, or that's actually really difficult to implement, and bring that over. But then a lot of the infrastructure that goes around it, the the dispatch and such, it may be better to rewrite. Um, when you're that far away from the workflow you would like, um, then there's frequently a case for rewriting those pieces. The challenge is, so usually within our funding cycles, it can be really difficult to justify, say, a year of no new science papers. So if rewriting is going to be a big task, the old model kind of has to stay operational. And maybe that's okay. Maybe it can go into maintenance mode and people can continue working with that. Um, an advantage of doing things incrementally is you stick with one code base. You can keep publishing the new science papers. The people involved in that um, get to keep using the latest version, and their workflow gradually gets better. So the software development cost may be higher, but the social aspects and getting people to sort of gradually upgrade may actually make it more sustainable. That's why it's a really delicate issue.
Matt makes an interesting point that we forget that testing is a large portion of code development. When we think about code, and we often think about just writing the lines of code, but testing is a huge portion of what we should be doing, at least.
Yeah, testing is coming up with good test cases is hard, especially when it requires a. So it's actually common to be, say, working in a library, and the best uses of the library are other projects that you might not even like, but certainly you can't just merge their code. It could be a different license. It's too much code. It's not maintainable for you. So you get that external testing, but that external testing is kind of expensive relative to unit tests that you have within your project, because it involves other people.
Matt, are you referring
So,
to the codes themselves? You say best ones.
I think he's referring to the tests. Yeah.
Test. Okay.
So that is absolutely common. So we build libraries, even end user packages, but the examples in those packages are not the most demanding runs. And the most demanding cases probably require an expert just to get it configured. It's not really something that is supportable. Because it might be expensive or it's kind of fragile. It's part of what made it cutting edge. If someone didn't invest all their time in making it distributable, So
I think one point to be made with regards to test, I don't know if it's with regards to regression tests, but test in general is that, by making them known, we have more confidence in the author's work. So it does benefit them to, document what these tests were and how they validated their codes.
Yeah, so I think in general, the community has to work on an incentive structure to to help people justify putting some effort into making their results reproducible. And so if that were the case, then we would have more of these kind of cutting edge science configurations that we could use as tests, that we could evaluate robustness of new methods, for example. But as it is, that incentive structure usually isn't there. It's often a lot of work for the most cutting edge cases. And so it ends up not getting done. So Patrick had a comment earlier about kind of separation of concerns, this idea, do one thing and do it well. So in the Unix world, that there's a significant ecosystem of tools that basically operates on text streams. And so this concept, everything is text, is it ends up being really practical. It's not always optimal, but it's very debuggable and kind of composable. So you can string together a pipeline that makes various changes, and it's something you can put together interactively. You can look at the intermediate results easily, and an interactive environment especially, that's really handy. In high performance computing, I would say that the right ideal is to package a component as a library with an in-memory interface. So be able to pass data along in memory buffers of sorts, and get the diagnostics and whatever else that you need out. And so part of that is to expose parallelism. So we can't use streaming, even if we wanted to. Streaming one parallel job into another serializes it. And that serialization, then you lose all opportunity to get better performance.
Okay, so we've gone over the hour. I don't see any active typing. Patrick is going to now. Okay, great. So again, I'd like to thank Jed for pulling an all-nighter to being with us today and talking about the best practices we should all be using in our work. And to remind you that our next webinar will be in January. It will be with Louise Kellogg and Peter Ariel. They'll be discussing their benchmarking work in mantle convection in their joint talk, Influence of Numerical Discretization on Preferred Thermal Convection Patterns in a 3D Spherical Shell. So as always, more information can be found on our website, and this webinar will also be posted on our website for later viewing. Thank you, everybody, and have a good afternoon.
Thanks, Lorraine.